Good morning. Do we have any questions before we get going here? Well, we've been talking about storage devices, RAM, SRAM, DRAM, all those kind of good things. And then we started talking a little bit about disks, and we noted that we have these latencies associated with accessing a sector on a disk where you have to seek, move the arm out to the right track, and then you have to wait for the proper sector to rotate around. So you have that rotational latency, and then you have the time that it takes to actually transfer the data as the sector rotates underneath the read write head. So you can look at some numbers associated with these things, and these are roughly realistic numbers or whatever. For the seek time, obviously it's going to be different if you're seeking, one track over, two tracks over, as opposed to going all the way across the surface of the platter. So how do you come up with an average seek time? So they basically, the manufacturers run these tests where they feed a random sequence of requests at the thing, and then they look at all the seek times and they take the average of all that, and that's what they publish as their average seek times. But any one particular request that you make to the disk is going to vary from that, obviously, depending on how far it has to go. There is a phenomenon going on where when it's sitting still, to get it up to the speed that it needs to travel, there's a little ramp up time and an inertia there, and then once it's up at the speed that it actually travels at, it goes pretty fast across the tracks, and then you got to slow it down and bring it back down to zero, and then wait for the head to quit settling. So it's cheaper per track to do a big, long, huge seek, than do a track to track kind of seek. So they publish on the specs on these drives. You can look at them on there. It'll show you the track to track seek time, and it'll show you the average seek time, however they computed that. So anyway, we're just saying, oh, suppose it's 3 to 9 milliseconds is what the average seek time looks like, and then if the thing was spinning at 7,200 RPMs, what would be the rotational latency? And on that, for an average, you just say, well, everything else being equal, randomly, which sector are you after? I got to wait half a rotation on average, maybe, for the thing to roll around. So that's what you'd use for that. So half of, you know, 1 over the RPMs at 7,200 RPMs. And then the transfer time that's going to depend on how many sectors per track there are. And of course, the sectors per track varies depending upon which recording area it's in. So that's a little bit of a fuzzy thing there, too. But you kind of estimate it with the average number of sectors per track on the whole disk. And you can come up with some numbers for these figures like 400 average sectors per track with a 9 millisecond seek time running it at 7,200 RPMs. You'd end up with something for the total access time being the sum of the seek latency, the rotational latency, and the transfer time. So the moral of the story, of course, being that the access time is totally dominated by this first number here. The seek time is the real killer. So you get expressions like, oh, the first bit in the sector is the most expensive, the rest are almost free, right? So once you get there and it rotates around, transferred is not a big deal. And so then you do the comparisons to typical SRAM speeds, and you see that it's about 40,000 times slower to get data off of that disk drive than it is to get it out of SRAM memory, and about 2,500 times slower for the DRAM. So it's a huge difference. And so we obviously want to come up with schemes where we can keep things that we need in memory and not have to go to the disk, if at all possible, to get them. The other thing that goes on with these disks these days is to really address a sector, you'd need those three components: the cylinder, the surface, and then the sector within the track. And that depends upon the physical geometry of the drive, right? Well, in the software, the driver might be nice. We didn't have to bother with knowing the individual geometry of every possible disk drive you might hook up to the computer and deal with that. So in later versions of disk drives, all the current ones, they have a scheme called logical block addressing that is done by the drive itself, where you just treat the drive like it was a big linear array of blocks, and you give it a block number that you want, a sector that you want, and it does the conversion of that logical block address to a physical cylinder surface sector type of address to go get it. And that way, we just deal with one number for the drive. How big is it? And so the logical blocks go from 0 to however many you have, right? So all of the modern drives behave that way and have that logical block addressing mode. And that's typically what you'll see them being used for on your PC. Another trick that's going on with these modern drives is that in each recording region, which defines how many sectors per track there is in that region, they'll have some spares. So they'll put some spare cylinders in each region. And this is a fault tolerance consideration, because you don't want the whole drive to be worthless and unusable if you have one little spot on the platter all of a sudden that isn't working right and doesn't record properly. So they have a scheme where they can sub in these spares to replace one that might be failing. So there's a degree of fault tolerance, and that's all built into the logic and the electronics on the drive itself nowadays, because it's doing the logical block address translation anyway. And so it can keep track of when it has these spares that it's using for some particular physical location on the drive. And so the OS and the disk drivers and all those don't really even need to know about that. The drives just do that themselves now. So we expand our stickman picture of the computer, and we were looking at getting things out of memory, going across this IO bridge to the memory bus, but the IO bridge splits off in different ways, and it goes to the IO bus as well. And then you have things hanging off the IO bus, like your USB controllers, graphics adapters, disk controllers, and then you have these expansion slots out here, and they come in various flavors depending upon what generation motherboard you're looking at. The current ones are some flavor of PCI uh, thing, typically peripheral component interface standard, and it comes in several sub flavors for different generations of the PCI standard. So, in any rate, you've seen these things on your computer, probably these little expansion slots. The disk controller and all this crud typically these days is all built onto the motherboard and not a separate card, although you can have cards you put in there to put more disks on the computer. So the disk controller you can think of is accessed by the computer in two different ways. It could either be through what we call port addresses, which are separate from memory addresses, or it could be set up so that it is a memory mapped device, such that in certain addresses, rather than being latched into the main memory, would actually be diverted and responded to by this disk controller. So modern disk controllers tend to use the memory map scheme as opposed to the port access scheme. Um, in any event, there are some things you can think of as registers that live on the disk controller that we're loading with commands, little bit patterns that mean various commands. And then you feed the command to the disk controller, and then it goes out and does what you ask it to do on the disk. Go get me this particular logical block number X off of the disk. And then it loads it up into an internal buffer, a little chunk of memory it has inside the controller to hold that thing that it just read off the disk. So the thing shows here that we're accessing this disk controller either through port addresses or more modern way of through memory mapped IO addresses down there, feeding it the commands to do. And then it goes in and does the commands. And the command would be go get me some sector off the disk and load it into memory at this address that I gave you. So then the disk controller goes off and it does that all by itself and loads that stuff out of the read buffer here into the memory at the location you told it to put it, independently, therefore, of the CPU, right? Once you've loaded the commands in here to it, it goes off and does its thing, and it does what we call direct memory access or DMA transfer into the memory of the computer. So you see, we have multiple things now trying to get at the memory of the computer. We have the processor, and then we have some of these peripherals trying to go through the IO bus and the IO bridge to get at to put things in the memory of the computer. So these are what we call DMA channels, and your computer has a number of different DMA channels that can be used by these peripherals to shove things in there. But there's a traffic cop, right? Saying, oh, well, you're accessing that, then I can't get to it. And so that logic is built into that thing that we call the bus, right? Through this IO bridge. When multiple things are trying to access the bus at the same time, one of them is granted access by the bus controller chips, right? So then how does so the operating system said, oh, I need to go get something off the disk to satisfy this file read that this process wanted. And it set up a transfer of that sector into the memory, and the processor is off doing other things at this point because this is glacially slow operating this electromechanical device compared to the speed at which we can run things in the CPU, right? That factor of 40,000 that we were talking about, right? So obviously, we're not going to sit here and let the computer do nothing while this DMA transfer happens. So the OS is off running 14 different processes or whatever before this thing ever finishes, right? And then he has to tell the operating system somehow that, oh, I finished doing that transfer because you're off doing other work. And that's accomplished through an interrupt. So there is a pin on the CPU called the interrupt pin, one single pin on the thing. And when you toggle that pin, when you pull it down, at the beginning of every instruction cycle, the CPU looks to see if that pin is asserted, if there's an interrupt pending on the computer. And if there is, it goes through an interrupt acknowledge cycle. So the way this actually works is the disk controller, you can think of these lines coming up out of the bus here through the IO bridge, and they get to a thing ultimately that's called a interrupt controller chip. And it used to be a separate chip on the motherboard. Now a lot of this stuff is all sucked up into one chip, what we're called glue chips, where we have a lot of the functionality for these things all crammed into one chip to make it cheaper to fabricate these things. And so anyway, embedded in that glue chip is the old interrupt controller stuff, right? And the way it works is it has a table in there. And so there's a level of indirection involved here. The device has a line that's actually wired up to go to the interrupt controller chip. And then when that device yanks that line to the interrupt controller has a table with a number associated with that line. So there's two numbers really. There's a number of what's the line that it's hooked to, and then there's the number that's in that table. And so that provides us this level of indirection between the actual physical number and what we want to send to the CPU when we tell it that the interrupt has occurred. And that table gets loaded at boot time. When you boot up the computer and load the OS, some of the things it does to dust off the computer and get ready for open for business is loading up that interrupt controller chip table. And what the way this works is at the beginning of the cycle, it sees that the interrupt pin is asserted, and then it makes an acknowledgement signal to the interrupt controller chip. And the interrupt controller chip then takes the number out of that table and shoves it at the CPU down the address lines, actually. And the CPU latches that in, that number that the interrupt controller chip gave it. And then there's a register called a vector base address register that points to memory where we have a table lying in memory. And we take that number that the interrupt controller chip gave us and we use it as an offset into that table. And we pick up an address out of that table, and that is the address of the interrupt service routine that we need to go execute to service the interrupt that has been posted. So that's what we call an interrupt vector. Those entries in that table are the interrupt vectors that point at the interrupt service routines that are just some code laying in memory. That's part of the operating system so that the operating system can respond to the fact that that interrupt has been asserted on the computer, whatever it means, right? So that's physically how that operates. Questions about the interrupt service routines, the interrupt controller, all those concepts. So we also have some solid state disk drives now, right? And the solid state disk drive has a thing called a flash translation layer. We'll talk about what it does in more detail in a second. But we're basically trying to emulate the behavior of a disk drive where you could make requests to go get me some logical block off of the device. Go get me logical block 597 or something, right? Well, those blocks, those sectors worth of information actually live in these pages down here, right? And there's a little bit of strangeness about the way this works because what this thing is, of course, is just another form of electrically erasable read only memory. And so we want to read a sector, we actually go to the right block and then the right page within that block and then the right information within that page to get the right sector's worth of information in a buffer that we're going to then do the DMA transfer into memory, just like the disk device did, because we're just emulating the behavior of a disk here. But in order to write something in there, it's a little strange. What you have to do is you have to suck the whole block up into a buffer, and then you have to write what you want to change into the page where the change is going to happen. Then you have to erase the whole block. It's electrically erasable read only memory. And then you write out of the buffer back into the block that you erased. So that is what you have to go through when you do a write. You got to erase the entire block. So you pull the block into a buffer, you change what you want to simulate that you're writing to some sector of the disk, right? You erase the block and then you write the whole block back. So eventually, if you keep writing this block back over and over again after 100,000 times or so, whatever it is, the thing won't work right anymore. So there's some logic in this flash translation layer that when we're translating the logical block addresses onto where they live in these different physical blocks, can do a level of indirection and do what we call load leveling, so that we're not writing to the same place over and over and over again. It just spreads the wear across all the blocks somewhat uniformly, so that the device has a longer life before a failure occurs. So that load leveling is part of the logic in the translation layer, but it's the rest of the world outside of here is oblivious to that going on. You're just interacting with it like it's a regular disk drive, regardless of all these things that are internally going on. So when you look at the solid state drives and you look at their speeds, you'll see that the read speeds are a lot faster than the write speeds. And that's because of that phenomenon where you have to erase the whole block and then write it back with the change that you wanted to make in order to actually do a write. And the slowest thing in this whole process is that business of doing the erase of the electrically erasable read-only memory. Accessing it is a lot faster, just reading things out of it, than writing things into it. It's about twice as fast, I guess, or 10 times as fast for random locations that you would be trying to access. So it reads a lot faster than it writes. Unlike the rotating disk, where it doesn't make any difference, it has to spin the sector underneath the read write head, and it doesn't matter whether you're reading it or writing to it. It takes the same amount of time for that sector to traverse under the read write head. There's no difference in the read and the write time, but there is a difference on your solid state devices. So the trade-offs of the solid state devices versus the rotating disk is they're faster and they consume less power, and they're less prone to failure if you drop them on the floor. You drop a regular disk on the floor, you might ruin the whole thing. If you crash the read write heads and then one of the read write heads doesn't work anymore. So they're a little more rugged in that sense, and so they're kind of preferred in that from that to used in laptops and those kind of devices that are being carried around all over the place, as opposed to just sitting in a fixed location like a desktop computer. So the mitigating the wear stuff with the wear leveling logic, but eventually at some point it will eventually wear out. But then again, so would a rotating disk possibly, although it can withstand some errors due to this cylinder sparing and that sort of thing. So, you know, maybe they'll wear out slightly before a rotating disc would wear out, but it's going to last a pretty good long time. And so this figure is out of date. They are no longer 100 times more expensive per byte than a rotating disc. Maybe, twice as expensive, 4 times as expensive, those kind of ranges nowadays. You can get a terabyte solid state drive for about $100. Is a really good price on one of those. So for $100, you can probably get say a 4 terabyte rotating disk. So about 4 times as much storage per dollar, but no longer 100. It's really come down quite a bit. So they use these in all kind of mobile kind of devices, and they're beginning to see them also in desktop type computers that may have one solid state drive of like a 0.5 terabyte, and then it'll have a rotating disk that's bigger, so that kind of thing. So if you look back at 30 years of history and you look at the prices and the capacities, the speeds of all these different flavors of memory, you see some pretty incredible progress 30, well, now 40 years ago. Um, The price per megabyte of some transistor-based SRAM might have been $19,000, and it had 300 nanosecond access time. And so you look 30 years later in 2010, the price is 60 instead of 19,000. So that's a improvement of 320 times, right? It cost 1/320th per megabyte as opposed to what it cost back then. 320 times improvement. The access time is only improved like one and a half. 200 times because it's one and a half now, right? So not quite as much as the cost has come down, but that's still really good improvement. The DRAM, not so much. The cost has come way down from what it was, but the access has only improved by order of nine, 9 times. And the typical size has increased enormously of how much you would have on a particular system, possibly. The disks have improved price wise. The amount of storage per dollar has improved the most in the disks, right? And the access times have come down by about 30. And so the sizes have grown hugely, right? So the sizes have grown the most, and that's related to this fact that the price has come down the most. You'll hear people make these crazy, comparisons of, oh, if cars had improved the same rate that our computers have improved in 1980, if you bought a car for $19,000 in 2010, you ought to be able to buy a car for $60, and if a car could go 100 miles an hour here, it ought to be able to go 20,000 miles an hour here, right? So they hear those silly kind of comparisons, but it does drive home the point that these things have massively improved in capacity, speed, and price. But the one that isn't improving that much in terms of speed is this DRAM deal, right? And so that's kind of a problem. If you look at the CPU rates over time, back in 1980 on a 8080 processor, it's a precursor of an 8086 processor, you're looking at about 1 megahertz, cycle times 1,000 nanoseconds because it's 1 megahertz, right? And then you get all the way over here to 2003, a Pentium 4, you're looking at 3.3 gigahertz, right? So that's 3,300 times faster than that thing in that 23-year period. Got cycle time down to 0.3 nanoseconds, and it had one core. But then something strange happens between 2003 and 2005. You notice that it went from one core to two cores, but the clock rate dropped actually slower than it was over here. Well, why is that? Well, you could have kept making the clock rate faster and faster as you made the chips denser and denser, but it consumes more power that way. And when it consumes power, it dissipates heat. And so to get faster and faster from this point, you would have to have gone to active liquid cooling to cool the chip down to keep it from melting itself. So now the case for your computer costs 10 times what the computer costs, right? So that is an economically viable way to go. So rather than doing that, they said, well, we got all this extra density we can use on the chips. So we'll start putting more cores on the chip and we'll drop the clock rate down, reduce the overall heat dissipation and the power consumption. And we'll get an effective cycle time since we have two chips faster than the effective cycle time. But to do it, you're running two separate cores. So if you had one individual thread for one process running here, it would probably run faster than that same one thread running over here. But now I could have multiple threads going at the same time, right? So that's the trade-off. And over time, the trend you're seeing is this number just keeps getting bigger. We've got more and more cores that they're cramming onto the chips, but the speeds you're seeing are not going to get bigger than that 3.3 that they had way back in 2003. You can get some current, you know, processors that'll ramp up to in the 3 gigahertz range, but that's usually in what they call the turbo mode. The normal mode of running the chip is at a lower clock rate, using less power, dissipating less heat. And then when it gets really busy, it can detect that it's really busy, and then it can amp up its clock rate temporarily for little bursts and then drop it back down. So that's the way most of these processors now are built, especially the distant difference between the turbo speed and the normal operating speed is most noticeable on like a laptop, right? Where they really are concerned about heat and power dissipation. You don't want to drain your battery on your laptop, right? So they run the thing at a real slow clock rate, maybe 1 gigahertz or something. And then they'll ramp it up all the way up to 3 or 3.4 or whatever for short periods of time. But they want to have the normal speed that it's running at, not sucking a whole lot of power. The distances between the normal speeds and the turbo speeds on the processors that are designed to go in desktop machines is not quite as variable as it is in the ones in the laptops. So at any rate, we drop the speeds to use less power, dissipate less heat, and then we just keep adding more and more cores to get more and more throughput, right? So now you see the latest versions of like the Core i9 processor. You can get some versions of it, I think, have like 8 or even 12 cores on the chip, right? So anyway, that's the trend. But one thing that's going on here is that DRAM didn't get a whole lot faster. It only got faster by a factor of 9. So over time, even though we're getting the CPU speeds up faster and faster and the effective cycle times up faster, the distance, the gap between the CPU speed and the DRAM speed is actually getting bigger over time. This is becoming more and more and more of a problem as we make the CPUs faster. We can't really do anything to make these DRAMs faster. We've tried all these tricks, DDR, DDR2, DDR3, DDR4, and they keep trying all these tricks to inch it up a little and make it a little faster. But the gap is still growing between the CPU speed and RAM speeds. So, from one point of view, what good does it do you to keep making the CPU faster if you can't feed it the stuff out of memory any faster? And that issue is what we're going to discuss in the next part of the material in the chapter, which leads us to this concept of building caches. So, how do we deal with this? Well, locality to the rescue, right? The key to bridging the CPU memory gap is the fact that programs exhibit types of locality. So here's what we mean by that. We have two types of locality. Locality, it can be spatial locality, and it can be temporal locality. Spatial locality is if I access memory address X and then I immediately access memory address X plus one, they're right next to each other. They're spatially local to each other, as opposed to accessing something here and then something way off in memory, some other location. Temporal locality would mean I access this and then I come back later and access it again in the relatively near future, right? So that's temporal locality. Well, our programs, by just the nature of the programs and the nature of the fact that given anything else, the computer just walks from one instruction to the next across memory, they tend to exhibit to some degree or another, both temporal and spatial locality. If we look at a for loop, this array that we're accessing in the for loop, those locations are just right next to each other in memory, right? So that is spatial locality. We keep hammering the same sum. If it was a location in memory and this I was a location in memory, we just keep accessing them over and over again. In reality, those are probably in registers. So we're not even accessing memory. But if they were some local variable in your activation record on the stack for this function, whatever this function is, they would be hitting the same memory location. So they would exhibit locality. And the loop itself, if you think of the code laying in memory that we've got to do to execute the loop, we're cycling back around and running that same code, this same addition operator, right? It's being picked up out of the opcodes, right? So it's exhibiting temporal locality with this for loop. This is what we call a stride one reference pattern because we're accessing the exact next location in memory after location I. We go to I plus one, I plus two, I plus three. That's a stride one reference pattern, as opposed to something here and then something way over somewhere else in memory. That would be a bigger stride, right? So we want the holy grail here is to access things with a stride one reference pattern. That gives us the tightest spatial locality we can achieve. So if we look at this loop where we have a nested loop walking across a two-dimensional array, the question is, does this exhibit nice, tight spatial locality? And the claim here is being able to look at code and get a qualitative sense of its locality is a key skill for a professional programmer. So if you go back to the syllabus and look at the outcomes for the course, you'll see some language in there to the effect of the ability to analyze the degree to which a program effectively exploits the temporal and spatial locality of the computer. And you'll see another thing in there about the exploit the superscalar capabilities of the computer. So these are all different flavors of optimizations, really. When we write our code, how can we make our code run fast? We looked previously at doing some, code motion and various types of common optimizations. And we noted when we were doing that touching memory is the most expensive thing going. So if we could write code that could cut down on the lag that's going to happen when we touch memory by touching it into the areas in these caches that are operating faster than the DRAM operates, that's a really significant improvement in how fast our program is going to run. So it's an important skill to develop to be able to look at your code and to understand the degree to which your code is going to effectively take advantage of those caches, right? So this little loop here, is it exhibiting nice, tight stride one spatial referencing? Well, we know in C and every other language except Fortran that the thing is laid out in row major order in memory. And we're accessing the thing varying the rightmost subscript fastest. So all of the stuff for row I is laid out right next to each other. And so we're accessing within row I, right? And then we increment I to go to the next row, but then we vary the inner subscript fastest. So we're accessing the things within the I plus one row. So yeah, this is exhibiting nice, tight spatial locality because we know that the array is stored in row major order, and this is the proper way to touch every element and sum them all up. If we had it like this, where the J was on the outer loop and the I is on the inner loop, and it says IJ, what are we doing? Well, we're still visiting everybody in the array eventually, right? We'll get the same sum. the result doesn't change, but the speed at which this will run certainly is going to change. Because what are you doing here? You're holding I fixed. I mean, you're holding J fixed and you're varying I. So you're accessing the same column on all the rows. Walk down a column, right? So that is going in locations away in however many bytes it takes to hold one. I guess these are ints, right? So they're 4. So every time you increment that, you're going 4 in memory locations away from the last reference you made to this thing. So 4 in is a lot bigger than 4, right? Which is the actual next guy in the array, the next integer over, right? So this is not exhibiting that nice stride 1 spatial locality and will in fact run slower as a result of that if n and m get large. Okay. So then this one says, okay, now we've got a 3-dimensional array. Let's look if we can permute the way the loops are doing the accesses to make it run fast. So the sum is going to visit everybody in the 3-dimensional array eventually, but what's the order that we're going to visit them in? Well, the outer loop is I, the middle one is J, and the inner one is K, but notice those don't line up left to right here. And in row major order, you want to vary the rightmost subscripts fastest and then go to the left one, right? So to make this thing run fast, if it says A sub Kij, then this for loop here ought to pull it out to the outside and have Kij as the order of the loops so that it varies the subscripts the way that you want them to vary to get the tightest locality of reference. Does everybody see that? So this would definitely not, in general, run as fast as moving that outer for loop to be the one that varied the K, right? Alternatively, you know, since you're using the same in, you know, you could vary it differently in here. You could rearrange those. So, memory hierarchies, some fundamental enduring properties of hardware and software. Fast storage technologies cost more per byte and have less capacity and require more power, generate more heat. The gap between the CPU and the main memory speed, the DRAM memory, is getting wider and wider. Well-written programs tend to exhibit good locality. These fundamental properties complement each other, and they suggest an approach for organizing memory and storage systems known as the memory hierarchy. So you get this famous pyramid here, right? The fastest thing you got going is the registers up in the CPU. And that's the one you have the least of, right? The next thing you have is an L1 level 1 cache made out of transistor-based memory. It's fast, right? But it takes, as we've seen in our example processors we're using, these Core i7s, you've seen it takes 4 clock pulses, even if you hit in this L1 cache, to get it pulled over into the register. And then we have an L2 cache, which is bigger than the L1 cache, but slightly slower. And then on our processor, we actually have an L3 cache that's much bigger still, but slower. And then the 4th level in our processor is the main memory, the DRAM. And then you go down, okay, I got some disks, and then I've got some stuff across the network maybe. So you get this big pyramid of the least of it is at the top, the most of it is at the bottom, and the speed gets bigger as you go toward the top. It gets slower as you go toward the bottom. The price per byte gets lower as you go down and gets higher as you go up. So the fundamental idea then is to have some caches made out of fast memory technologies where I can bubble up things into these caches as I make references to memory so that hopefully the things I want have bubbled up through the caches. And if I reference things that are close to where I referenced before, or I go back and, like in that for loop, run the same instructions, those are sitting in my caches and I can get at them fast and I don't have to get them from the slower guys. So this is a sequence of hierarchies of bubbling things up toward the CPU into faster and faster memory caches with the hope that if my program exhibits temporal and spatial locality, that will make effective use of those caches. And the degree to which your program makes effective use of those caches is the degree to which your program exhibits temporal and spatial locality. So the thing you have to learn when you're writing your program is how can I write programs that make effective use of the caches by exhibiting the most temporal and spatial locality that I can. So that's another form of optimizing your code. And that one has dramatic impacts on how fast your code is going to run because the most expensive thing going is touching memory, right? So let's look at the real computer. That's not it. That's a file. Let's look at this. Here's old Schofield, right? And as we know, Schofield is a Core i7 Ivy Bridge processor. And on the Core i7 Ivy Bridge processor, we have three levels of caching. We have the L1 and the S2 cache. And it turns out at the L1, at the very top level there, right, it's bifurcated. We have two different caches at the L1 level, one of which holds instructions that are being fed into the CPU, right? The instructions to execute. And the other one holds data references that those instructions made, right? So we have 32K to cache up instructions being pipelined into the CPU and 32K to cache up recent locations that have been referenced in memory. And then we go down to the L2 cache. We have a lot more of it, but it's a little slower. We'll get the exact times for this processor, but I think they're sort of on the order of a 10 or 11, 12 maybe cycles versus 4, right? So we have 256K of that L2 cache. And then we go to the L3 and we have 8 megabytes of L3 cache, but it's slower still. It's probably up around maybe 30 cycles to get to things out of it. I'll get you the exact numbers for this CPU. And then we have, as you remember, 4 cores on this processor. Each one of them gets his own private L1 and L2 caches, but all 4 cores share a common L3 cache. So you got 4 pigs feeding out of the same trough there. And those 4 cores have their own sort of agendas, right, as to what addresses they're referencing, depending upon what thread they're running that is running some program over here in memory, and the other thread's running on this other cores running some program in some completely different amount of memory. So the amount of stuff that each of them wants to pull into the cache, they're sort of fighting for space in this common cache in the L3 cache, but they have their own individual agenda going on with the L2 and the L1 level caches. So we will look at writing programs and running them on this computer and see how effectively they utilize these exact sizes of caches that are available to us on that computer. So this is a skill you have to get in order to write effective programs. Remember the statement back here. Being able to look at code in a qualitative sense of its locality is a key skill for a professional programmer. And if you really want to optimize it, you have to get down to that specific processor. But fortunately, all of these Core i7s have pretty much the same cache profile. Some of the later ones might have a bigger L3 cache than this Ivy Bridge one, but in general, they're going to line up pretty much like 32K for each of the L1s and 256K for the L2. The size of the L3 will vary slightly. So that, we can optimize our code pretty effectively for that set of processors, but to optimize it for that specific exact processor is dependent upon some characteristics of that specific processor relating to the sizes of the cache. So any questions about this leading into this idea of creating caches of faster memory technologies? We're going to go in and see exactly how it works on this computer and how these caches behave and how they operate, and then we can relate to using them for our programs, see how our programs are going to run on them. So office hours are today at 1. Wednesday office hours are at 1, not 2. So if I don't see you then, I will see you tomorrow. So keep reading in your chapter and read a little bit ahead on how the caches work. So we'll hit it tomorrow morning and go into all the gory detail about how these caches work on this exact computer. Okay. Any questions before we go? So once the quizzes are all finished this afternoon, I'll get the latest snapshot of all the grades up that are available up to that point, and I'll run another distribution for you so you can see how you're coming along with relation to everyone else and where your clusters are falling. So we'll run the stats on that again, give you a latest reading with some more scores in there. Any questions about anything? So if I don't see you at 1, I will see you tomorrow morning. Have a great day.